Tonight we're going to follow Voyager 1 forward through time. 1 million years, step by step, and find out exactly where it ends up. You probably know the basics. Voyager 1 launched in 1977, crossed the heliopause in 2012, and today sits more than 24 billion kilometers from Earth. Still moving, still sending a signal home that takes over 22 hours to arrive. Most people picture Voyager as almost somewhere. After all this time, it has to be approaching another star, getting close to something. It is not close to anything. And when you follow the honest numbers all the way out to 1 million years, what you find is not arrival. It is something much quieter, much stranger, and much harder to sit with than most people expect. By the end of tonight, you will understand exactly where Voyager 1 ends up, what it passes on the way, and what that journey says about the size of the universe we actually live in. If you love this kind of patient, grounded space science, subscribe. It helps this channel reach more curious minds like yours. Now, let's begin. Most people who know Voyager 1 carry a mental image that is roughly correct but tilted in one important direction. They picture a sophisticated, purpose-built deep space vessel, something designed from the start to travel as far as possible, for as long as possible. A machine aimed at the stars from the moment it was conceived. The reality is more humble, and honestly more impressive for being so. Voyager 1 is about the size of a small car. Its central body is a 10-sided structure roughly 47 centimeters tall, and attached to it are booms, antennas, scientific instruments, and a large parabolic dish antenna, 7 meters across, that points back toward Earth. The whole assembly weighed about 722 kilograms at launch. That is lighter than a grand piano, and far lighter than you might expect for the farthest traveling object in the history of human civilization. It launched on September 5, 1977, from Cape Canaveral, Florida, aboard a Titan IIIe Centaur rocket. The mission had a defined purpose and a defined timeline. Voyager 1 would use a rare alignment of the outer planets, one that only recurs every 175 years, to perform a gravity-assisted flyby of Jupiter and Saturn. It would study both systems up close, return data, and then the mission would be complete. The original design life was 5 years. 5 years. That was the number written into the mission plan. It has now been nearly 50. What happened is that Voyager 1 kept working. The instruments stayed functional far past every specification. The power held. The signal kept arriving at the Deep Space Network antennas on Earth, year after year, faint but readable, and the mission kept expanding in the way the best scientific missions always do. Quietly, without ceremony, by simply continuing to function when everything expected it to stop. In March of 1979, Voyager 1 made its closest approach to Jupiter, flying within 349,000 kilometers of the planet's cloud tops. The data it returned changed our understanding of the Jupiter system permanently. The Great Red Spot, which astronomers had observed through Earth-based telescopes for 3 centuries, was revealed as a storm of extraordinary internal complexity, with layered wind structures and dynamics no ground-based telescope could resolve. The volcanic activity on Io, Jupiter's innermost large moon, was discovered during this flyby. Nobody had predicted it. Before Voyager 1, Io was expected to be a geologically dead, cratered body similar to our own moon. Instead, it turned out to be the most volcanically active surface in the solar system, with sulfur plumes rising hundreds of kilometers above its terrain and constantly resurfacing the landscape. Europa, another of Jupiter's large moons, showed a surface of cracked, refrozen ice with almost no impact craters, suggesting that something beneath the ice was warm enough to resurface it regularly and erase the evidence of ancient impacts. That single observation from 1979, those long fracture lines across a smooth, icy moon, has driven decades of scientific attention. It is now the primary target of a dedicated NASA mission launched in the 2020s, more than 40 years after that first flyby. In November of 1980, Voyager 1 made its closest approach to Saturn, passing within 121,000 kilometers of the cloud tops. The ring system, which from Earth appears as a few smooth, broad bands, was revealed to contain thousands of individual ringlets, gaps carved by the gravitational resonance of inner moons, braided structures nobody had predicted, and spoke-like features that rotated with the planet's magnetic field in ways that physicists spent years trying to explain. Titan, Saturn's largest moon, was found to have an atmosphere denser than Earth's, thick with orange nitrogen haze so opaque that Voyager's cameras could not see the surface beneath it at all. The volume of data returned from Titan alone justified the entire mission. After Saturn, Voyager 1's planetary mission was complete. Its trajectory, shaped by Saturn's gravity during the flyby, sent it upward out of the plane of the solar system at a steep angle relative to the ecliptic. There were no more planetary flybys planned, no more rendezvous of any kind. The mission in its original conception was over. And yet the spacecraft kept going. Scientists at the Jet Propulsion Laboratory kept listening, and over the 4 decades that followed, Voyager 1 transformed from a planetary explorer into something nobody had quite planned for. The first human-built object to cross into the space between stars. Today, Voyager 1 sits more than 24 billion kilometers from the Sun. To make that number feel real, consider the unit astronomers use for solar system distances, the astronomical unit, or AU. 1 AU is the average distance between Earth and the Sun, about 150 million kilometers. Light from the Sun takes about 8 minutes to cross that distance and reach Earth. Voyager 1 is currently more than 160 AU from the Sun. The light that reaches it left the Sun over 22 hours before it arrives. The signal Voyager 1 sends home, traveling at the speed of light, takes that same 22 hours to reach Earth. When engineers at JPL send a command to Voyager 1, they wait 44 hours for the full round trip, 44 hours at the speed of light, just to say something and receive a response. No human conversation in history has ever been conducted at this level of delay. It is science carried out on the time scale of plate tectonics. Sit with that for a moment. A signal moving at 300,000 kilometers per second, faster than anything in the universe, still takes 22 hours to get there. That is how far away it is. That is where Voyager 1 is today. The farthest human-made object ever placed anywhere. The most distant thing our species has ever sent into the universe. And it is nowhere near another star. Nowhere near another star. Nowhere near, not approaching one, not partway to one. Not in any meaningful sense closing in on anything. The nearest star system to our Sun, Alpha Centauri, sits about 40 trillion kilometers away. After nearly 50 years of travel, Voyager 1 has covered roughly 0 to 0.06% of that distance. If a journey from Earth to Alpha Centauri were a 100-metre sprint, Voyager 1, after 50 years, has run about 6 centimetres. That gap between the two facts, farthest human-made object in existence and nowhere near another star, is what tonight is really about. That gap is where the actual scale of this universe lives. We are going to walk through it completely, step by step, over the course of 1 million years. The question that carries us forward is simple. Voyager 1 has been moving for nearly 50 years. It will keep moving for millions more. So in 1 million years, exactly, and honestly, where does it end up? To answer that, we need to first understand what 17 kilometers per second can actually accomplish, because the number sounds fast. It is fast. And against the distances between stars, it is very nearly nothing at all. It is a machine that kept going when nothing expected it to. That, before anything else, is what Voyager 1 is. 17 kilometers per second. That is Voyager 1's current speed relative to the Sun, sustained, continuous, and maintained without fuel, since the spacecraft has nothing to push against and nothing to slow it down. To understand what that speed actually means, consider this. A standard rifle bullet travels at about 0.9 to 1, 7 kilometers per second, depending on the firearm and the ammunition. Voyager 1 moves 10 to 20 times faster than a bullet. A commercial passenger jet cruises at approximately 0.25 kilometers per second at altitude. Voyager 1 is 68 times faster than that jet. The fastest human-made object ever recorded at a single point in time was the Parker Solar Probe, which achieved about 192 kilometers per second during its closest approach to the Sun in late 2024. Voyager 1 does not reach that speed, but Voyager 1 sustains its speed indefinitely without fuel, because in interstellar space there is nothing to push against and nothing to slow it down. No air resistance, no significant gravitational drag from any nearby object. It simply continues at 17 kilometers per second, because there is no reason for it to do anything else. 17 kilometers, every single second, for decades. Still going now as you listen to this. In one day at that speed, Voyager 1 covers about 47 million kilometers. In 1 year, approximately 537 million kilometers. Measured against the solar system, those numbers are genuinely large. At Voyager's speed, you could travel from Earth to the Moon in about 6 hours, Earth to the Sun in about 3.5 days, Earth to Jupiter at average distance in roughly 2 years, and Earth to Pluto at average distance in about 8.5 years. But now step outside the solar system, and here is where the arithmetic begins doing something very uncomfortable to your intuitions. The nearest star system to our own is Alpha Centauri, a gravitationally bound triple star system sitting about 424 light-years from Earth. 1 light-year is the distance light covers in 1 year. Traveling at 300,000 kilometers per second, that distance is approximately 9.46 trillion kilometers. So Alpha Centauri sits roughly 40 trillion kilometers from Earth. At Voyager 1's speed of 17 kilometers per second, how long would it take to reach Alpha Centauri? About 73,000 years. Not 730, not 730,300, 73,000 years. For the nearest star system. For context, 73,000 years ago our ancestors had not yet developed written language. The last ice age had not reached its maximum extent. Neanderthals still lived alongside early modern humans. Every city ever built, every empire ever raised, every book ever written, every scientific discovery ever made, every war ever fought in all of recorded human history fits into approximately the last 13% of that time frame. And Voyager 1 is not even heading toward Alpha Centauri. It is heading in a completely different direction, roughly toward the constellation Ophiuchus in the northern sky. The Alpha Centauri figure is purely illustrative, a baseline for what 17 kilometers per second accomplishes against the distances between stars. The answer in plain terms is not enough, not quickly, not in any time scale that connects to human experience. Let's build this out more carefully. 1 light-year is 9.46 trillion kilometers. Voyager 1 covers about 537 million kilometers per year. To cross 1 full light-year at that rate, Voyager 1 needs approximately 17,600 years. 17,600 years per light-year. Scale that up. The nearest stars are 4 light-years away. That is roughly 70,000 years at Voyager's speed. The center of the Milky Way is about 26,000 light-years from Earth. Reaching it from here would take approximately 480 million years at Voyager's pace. The diameter of the Milky Way is about 100,000 light-years. Crossing it in a straight line would take about 1.76 billion years. The observable universe is roughly 93 billion light-years across. At Voyager's speed, crossing it would take over 1.5 trillion years. The universe itself is only 8 billion years old. A Voyager speed crossing of the observable universe would take more than 100 times the current age of the universe. These numbers are not meant to produce despair. They are meant to calibrate. They are meant to give you an accurate picture of what interstellar space is, measured against what we can currently build. Voyager 1 is one of the greatest technical achievements in human history. It is also, against the backdrop of the galaxy, moving at something that can only honestly be called a crawl. Both of those things are true at once. The achievement is genuine and worth honoring. The scale is also genuine and worth understanding. Holding both simultaneously is the only honest way to think about the distances between stars. You don't need to understand all of this at once. Let it settle. The universe doesn't need you to rush through this. It has been here for 8 billion years. Now, before we follow Voyager 1 forward through those distances, there is something we need to clear up. Something most coverage of the Voyager mission gets subtly wrong. In 2012, NASA announced that Voyager 1 had left the solar system. That statement requires careful examination because the truth is more interesting and more complicated than the headline. In August of 2012, scientists confirmed that Voyager 1 had crossed the heliopause. The announcement traveled through every major news outlet. Voyager 1 had left the solar system. The headline was repeated around the world, and it was not entirely wrong, but it was missing something important, and the missing piece changes everything about how you understand where Voyager 1 is and where it is going. The heliopause is real. It is the outer boundary of the heliosphere, the enormous bubble of charged particles that the sun blows continuously outward in all directions. The solar wind, a stream of electrons, protons and heavier ions flowing outward from the sun's upper atmosphere at speeds between 400 and 800 kilometers per second, fills the space between the planets and interacts with the magnetic environments of every body it encounters. The heliosphere has an outer edge where this solar wind eventually loses pressure against the resistance of the interstellar medium, the thin gas and dust that fills the space between star systems. That outer edge is the heliopause. Outside the heliopause, the sun's wind no longer dominates. The interstellar medium takes over. The types and energies of particles change measurably. The magnetic field structure changes. Voyager 1's instruments detected exactly these transitions in 2012, confirming it had crossed from the domain of the solar wind into the domain of interstellar space. That crossing is genuinely historic space. That crossing is genuinely historic. It means Voyager 1 became the first human-made object to enter the interstellar medium. No spacecraft had ever done that before. But here is what the headlines missed. The solar system does not end at the heliopause. The heliopause is a particle physics boundary, the outer edge of the sun's wind, but gravity has a much longer reach than the solar wind. The sun's gravitational influence extends far beyond 120 astronomical units, where the heliopause sits. It extends to thousands of AU, and in fact to tens of thousands. Objects orbit the sun at those distances. They do so slowly, on paths that take millions of years to complete one circuit. But they are gravitationally bound to our star. They are part of the solar system in the only sense that ultimately matters. They move because the sun pulls on them. The gravitational boundary of the solar system is defined by the Oort Cloud. The Oort Cloud is the solar system's outermost structure. It is different in character from everything else we associate with the solar system. The planets orbit in a relatively flat disk, aligned with the sun's equatorial plane. The asteroid belt lies in that same plane. The Kuiper belt, which extends from about 30 to 50 astronomical units and contains Pluto, along with hundreds of thousands of icy bodies, also lies roughly in that plane. These are all disk-shaped structures. The Oort Cloud is not a disk. It is a sphere, or more precisely, a rough spherical shell surrounding the entire solar system in every direction, above and below the plane of the planets as well as outward from it. Its inner edge begins at approximately 2,000 astronomical units from the Sun. Its outer edge extends to somewhere between 50,000 and 100,000 astronomical units. In light years, that outer edge sits roughly 1.5 to 2 light years away from the Sun, almost halfway to the nearest star. Let that land properly. The nearest star to our Sun, Proxima Centauri, is full 24 light years away. The outer edge of our own solar system, defined by where the Sun's gravity finally gives way to the gravity of the wider galaxy, reaches approximately 2 light years. Our solar system takes up nearly half the distance to the nearest star. When you draw an imaginary line between our Sun and Proxima Centauri, the solar system occupies close to half of it. Every diagram of the solar system you have ever seen, the ones with 8 planets, an asteroid belt, and perhaps a thin disk of Kuiper belt objects at the edge, is showing you approximately the inner 1% of the solar system's actual spatial extent. The Oort Cloud, which accounts for nearly all of the remaining space, almost never appears. If it did, drawn to the same scale as those diagrams, The Sun and all its planets in the entire Kuiper belt would be a dot at the center too small to see with the naked eye. Voyager 1 crossed the heliopause at about 120 AU in 2012. The inner edge of the Oort Cloud begins at approximately 2000 AU. At Voyager's speed, the journey from 120 AU to 2000 AU. At Voyager's speed, the journey from 120 AU to 2000 AU takes about 300 years. Sometime around the year 2300, Voyager 1 will enter the Oort Cloud proper, and then the real crossing of the solar system begins. Not the poetic crossing, not the poetic crossing, not the particle physics crossing. The gravitational one. How long does it take to cross the Oort Cloud from inner edge to outer edge? At Voyager's speed, somewhere between 14,000 and 28,000 years, depending on which model of the cloud's outer extent you use. A central estimate is roughly 20,000 years. After those 20,000 years, Voyager 1 will have left the solar system in the complete gravitational sense. The Sun will no longer hold anything around it. It will be in true interstellar space. That is the real edge, not the heliopause at 120 AU. The Oort Cloud, extending to nearly 2 light-years, is the true outer boundary of the Sun's domain, and Voyager 1 has not even reached it yet. What exactly is the Oort Cloud? What does Voyager 1 move through for those 20,000 years of crossing? Those are the questions we follow next, because once you understand what the Oort Cloud actually is, what Voyager 1 is heading into comes into much sharper focus. If you're still with us this far tonight, this channel was made for you. A quiet subscribe helps more people find these kinds of evenings. The Oort Cloud has never been directly observed. State that plainly, hold it in mind, because it shapes everything that follows. We have never photographed an Oort Cloud object. No telescope currently in existence, no matter how powerful, has detected one directly. The objects in the Oort Cloud are too distant, too small, and too dark. They do not generate their own light. They reflect sunlight, but at distances of thousands to tens of thousands of astronomical units. Even a body several kilometers across reflects so little sunlight back toward Earth that it is indistinguishable from the background darkness. We cannot see them individually. We may not be able to see them individually with any instrument we are likely to build in the near future. Everything we know about the Oort Cloud comes from inference, and primarily from one type of inference: long-period comets. Long-period comets are comets with orbital periods of thousands or millions of years, which occasionally fall into the inner solar system where we can observe them. What is distinctive about them, considered as a population, is their distribution. They arrive from all directions, not only from the flat plane where the planets orbit. A source of objects that distributes things evenly in all directions is a sphere, not a disk. That was the key observation. Jan Oort, a Dutch astronomer working in the early 20th century, proposed in 1950 that the solar system must be surrounded by a vast, roughly spherical reservoir of icy bodies at enormous distances from the Sun. These objects, he argued, were the source population for long-period comets. Occasionally, one of them is gravitationally disturbed by the passage of a nearby star, by the large-scale gravitational field of the Milky Way, or by the tidal forces of a passing molecular cloud, and its orbit is nudged inward. Over thousands of years it falls toward the Sun, accelerating as it approaches, and eventually appears in our sky as a long-period comet. The brilliant comets visible to naked-eye observers throughout history, the ones ancient peoples recorded as omens and wonders, were in many cases objects making their first pass through the inner solar system after billions of years of quiet orbit in the Oort Cloud. The Oort Cloud on this model is a fossil, a remnant of the materials that built the solar system 4.5 billion years ago, that were scattered outward by the gravitational forces of the giant planets, particularly Jupiter, during the early violent period of the solar system's history. The objects there have been in deep freeze ever since, circling the Sun so slowly and so far away that nothing has disturbed most of them in the entire history of the solar system. Current models estimate that the Oort Cloud contains somewhere between 100 billion and several trillion individual objects. That range is large because we cannot observe them directly and must work backward from comet arrival rates from the expected efficiency of the scattering processes that place them there. and from the theoretical structure of how planetary formation and migration would have affected the outer solar system. Even the most conservative estimate, 100 billion objects, makes the Oort Cloud more populous in terms of object count than the total number of stars in the Milky Way. But here is the crucial thing about those hundreds of billions of objects. They are spread across a volume of space so vast that the average distance between any two randomly chosen Oort Cloud objects is billions of kilometers. The cloud is not dense. It is not a structure you would notice if you were inside it. It is a near-perfect vacuum in which dark icy bodies are separated from each other by distances that dwarf anything in the inner solar system. To make that feel real, consider this. The asteroid belt between Mars and Jupiter is often depicted in films as a crowded, dangerous field of tumbling boulders. Spacecraft fly through it routinely and never come close to hitting anything, because the average separation between asteroids is about 1 million kilometers. The belt looks dense on a diagram because diagrams compress space enormously. In reality, it is almost entirely empty. The Oort Cloud makes the asteroid belt look like a traffic jam. The objects in the Oort Cloud are separated from each other by distances that are orders of magnitude larger than the separations in the asteroid belt. If you were somehow positioned inside the Oort Cloud and looked around in every direction with the most sensitive telescope ever built, you might, with effort and knowledge of exactly where to look, detect a faint cold object at enormous distance. You would not see a cloud. You would see what appears to be empty space with very occasionally an unimpressive dark speck somewhere at the edge of detectability. Voyager 1 will move through this structure for approximately 20,000 years. The probability of it actually colliding with an Oort Cloud object during that transit is negligible, somewhere in the range of a few chances in a billion. It will pass through the Oort Cloud in the same physical environment it is in now, in near total isolation, encountering nothing. The distinction between being inside and outside the Oort Cloud is purely gravitational. Inside the cloud, the objects surrounding Voyager, however invisible, however distant, however uncountable, are gravitationally bound to the Sun. They orbit it. Outside the cloud, the objects one encounters are not bound to anything in the solar system. They belong to the open galaxy. During those 20,000 years of crossing, the Sun will slowly change in Voyager's sky. At the inner edge of the Oort Cloud, the Sun is still the brightest star by a considerable margin. A brilliant point of light, but not a visible disk. Not a source of any warmth detectable by instruments. Just the most luminous point among thousands. As Voyager moves deeper into the cloud, the Sun dims steadily and gradually. Somewhere partway through the crossing, it becomes merely one of the brighter stars, not dramatically different from dozens of others. By the outer edge of the Oort Cloud, the Sun is a faint point that requires knowing where to look to find it among the general field. At some moment during that crossing, the Sun becomes just another star. There is no event to mark it. There is no one aboard to notice. The spacecraft keeps moving at 17 kilometers per second through a darkness that looks identical in every direction. After the Oort Cloud, Voyager 1 is in the interstellar medium in the complete sense. No more connection to the solar system except the trajectory given to it at launch. And somewhere in that open interstellar space, roughly 40,000 years from now, the only event that will ever appear on Voyager 1's path is waiting. In 1977, a committee of scientists and artists gathered in Ithaca New York. Carl Sagan, the astronomer and science communicator who had become one of the most recognized scientific voices of his generation, chaired the group. Their task was unlike anything scientists had been asked to do before. They needed to design a message, a physical message that could survive indefinitely in space, communicate something meaningful about life on Earth to any intelligence that might someday encounter it, and do all of this without knowing anything about the potential recipients, not their biology, not their sensory systems, not whether they experience sound, light, or mathematics in ways recognizable to humans, not even whether they existed. The committee had to design for an audience that might be nothing like us, or might not exist at all, or might find the message in 1,000,000 years or 1,000,000,000. What they produced is called the Golden Record. The Golden Record is a 12-inch gold-plated copper disc. Both Voyager 1 and Voyager 2 carry one, encoded on the disc as analog audio signals are 116 images of Earth, greetings spoken in 55 human languages, and an audio program of approximately 90 minutes, which includes natural sounds from the planet, music from across human cultures, and a spoken greeting from the Secretary-General of the United Nations at the time, Kurt Waldheim. The natural sounds are extensive. Wind moving through trees, rain falling on a surface, thunder, ocean surf breaking on a shore, the songs of birds, including various species chosen to represent the diversity of avian calls. The calls of humpback whales recorded in the open ocean. A cricket on a summer night. A frog calling from a pond. A human heartbeat, and a mother speaking her first words to a newborn child. The music was selected with considerable debate. The committee chose Johann Sebastian Bach's Brandenburg Concerto No. Ax, 2 in F major, the first movement, played at a tempo the committee found especially alive. Beethoven's Cavatina from String Quartet No. 13 in B-flat major. Louis Armstrong performing Melancholy Blues. Chuck Berry performing Johnny B. Platt. Good, which Carl Sagan chose partly because he found it genuinely appropriate and partly because he found it funny to include rock and roll as a formal representative of human music, and nobody on the committee could construct a convincing argument against it. A Navajo night chant. Azerbaijani bagpipe music. Georgian polyphonic chanting from the Caucasus. Peruvian panpipes. A Japanese shakuhachi piece. An Australian Aboriginal song, music from Senegal, Bulgaria, India, and multiple other cultures, chosen to represent the breadth of human musical production rather than the preferences of any one tradition. Druyan, who served as creative director for the project and later married Sagan, proposed that she record her own brainwaves and include them. She sat in a recording studio connected to a brainwave monitoring device and thought about the history of the Earth, about the experience of falling in love with Carl Sagan, which had happened recently, and about what it meant to be a human being at this moment in history. Those brainwaves were converted to audio and encoded on the disc. If any intelligence ever finds the record and plays it, Andrew Leanne's thoughts from 1977 will be part of what they receive. Carl Sagan's son, Nick, who was 6 years old at the time, recorded the greeting that was eventually chosen to represent the children of Earth. He said, "Hello from the children of planet Earth." It is on the disc. The record is housed in an aluminum jacket that protects the copper from damage by interstellar dust. On the outside of the jacket are engraved instructions for playing the record, encoded as symbolic diagrams intended to be interpretable without any shared language or cultural reference. The diagrams indicate the correct rotational speed for playback, the physical format of the encoding, and how to construct a stylus to read the grooves. A stylus is included in the package. The assembly was as carefully designed as the committee could manage to be comprehensible to any intelligence that might encounter it, regardless of what that intelligence looks like or how it processes information. The Golden Record is one of the most genuinely moving objects our species has ever produced. It is also, if we hold to honest standards, almost certainly a gesture that will never be received by any intelligence. The probability of any civilization ever finding Voyager 1 in the void between stars, recognizing it as an artifact rather than as natural debris, retrieving it intact, decoding the symbolic instructions on the jacket cover, constructing a device to play it, and then deriving meaningful information from the sounds and images is extraordinarily small. Not zero in principle, just small enough that it cannot honestly be described as a realistic plan. It is more like a ritual, a way of marking the moment. The record was as much for the people who built it as for any imagined recipient. It was a way of saying, we were here, we knew we were alive. We knew the universe was large and that we were small in it. These are the things we loved. These are the sounds of our world. We wanted that to exist somewhere, even if nowhere anyone could hear it. What matters from a purely physical standpoint is what happens to the record over very long timescales. Copper is a durable material. The gold plating protects its surface from oxidation. In the vacuum of interstellar space, with no water, no oxygen, no biological agents, and virtually no mechanical stress, the record will degrade extraordinarily slowly. The primary damage mechanism is cosmic ray bombardment, high-energy particles streaming through the galaxy that damage materials at the atomic level over long timescales. But the timescales involved are enormous. Estimates suggest the record may remain substantially intact for hundreds of millions of years. Some estimates reach into the billions. It will outlast the spacecraft structure around it. It may outlast everything we have ever built on Earth. In roughly 5 billion years, the Sun will exhaust the hydrogen in its core and begin expanding into a red giant. Earth will become uninhabitable well before the expansion reaches it. Every physical trace of human civilization, every building, every monument, every hard drive, every fossil that preserves any biological record of the organisms that lived on this planet, will eventually be destroyed as the solar system transforms. Voyager 1 will still be moving tens of thousands of light-years from the solar system's original position, carrying a gold-plated disk from a world that no longer exists, built by a species whose fate by then is unknown. The disk will outlast Earth. That is not poetry. That is a straightforward consequence of what copper is, what gold is, and what the vacuum of interstellar space does to materials over time. But between now and that deep future, there is one nearer-term event to follow. In roughly 40,000 years, something will appear in Voyager 1's path. The only thing that ever will. But before that encounter, there is one more threshold to cross. Because at some point in this decade, Voyager 1 will go silent. At some point in the next few years, Voyager 1 will transmit its last signal to Earth. The timing is not known with exact precision, but the physics that determines it is well understood, and the outcome is not in question. Voyager 1 is not powered by solar panels. At the distances it travels, sunlight is completely inadequate for this purpose. Earth receives about 1,361 watts of solar power per square meter. At Jupiter, that number drops to about 51 watts. At Saturn, about 15 watts. Voyager 1 is now more than 160 times the Earth-Sun distance from the Sun. The solar flux there is so faint that solar panels of any practical size would generate almost nothing useful. Instead, Voyager 1 is powered by 3 radioisotope thermoelectric generators, known as RTGs. Each RTG contains pellets of plutonium-238, a radioactive isotope that decays by emitting alpha particles. Alpha decay releases heat steadily and predictably over many decades. That heat is converted to electricity by thermocouples, solid-state devices that generate a small current wherever there is a temperature difference between two connected materials. There are no moving parts, nothing rotates, nothing pumps, just heat on one side, cold space on the other, and a steady trickle of electrons. Plutonium-238 has a half-life of about 7 years. This means that every 7 years, half of the remaining plutonium has decayed, the heat output halves, and the electrical power drops by half. At launch in 1977, Voyager 1's 3 RTGs together produced about 470 watts of electrical power. Nearly 50 years later, they produce roughly 240 to 250 watts, and the number continues to drop by about 4 watts per year. To put that in terms that connect to ordinary experience, a standard incandescent light bulb requires 60 watts to operate. Voyager 1's entire available power budget today is enough to run approximately 4 of those bulbs. With that power, it must run its remaining active science instruments, maintain heaters that keep critical electronic components from freezing to temperatures at which they fail, power the transmitter that sends its signal back to Earth, and operate the onboard computers that manage all of these systems simultaneously. 4 light bulbs worth of power for everything. NASA engineers have been managing this shrinking budget for decades by systematically shutting off systemics that are no longer essential. The cameras were among the first casualties, turned off in February 1990 after the pale blue dot photograph was taken. Several science instruments were powered down over the following years. Heaters for certain components have been disabled, allowing those parts of the spacecraft to operate at temperatures well below their original design specifications, accepting some increased risk of failure in exchange for more power available to the instruments that remain active. At some point, there will not be enough power remaining to maintain the heaters that keep the remaining active instruments above their failure thresholds, or to power the transmitter, or to run the onboard computers reliably. When those thresholds are crossed, the scientific mission ends. The transmitter goes dark. The last signal, carrying whatever data it carries in those final hours, makes its 22-hour journey to the antennas of the deep space network on Earth, arrives, is received, and then there is no more. What remains is only the object, a mass of metal and glass and wire, moving at 17 kilometers per second, unable to send or receive anything, aware of nothing, carrying its golden disk through space that has no particular interest in it. There is something worth sitting with in this transition. For nearly 50 years, Voyager 1 has existed in two simultaneous ways. It has been a physical object moving through space, and it has been a source of ongoing information arriving on Earth. Scientists at JPL have known within small margins where it is at any given moment, how fast it is moving, what the local particle environment reads, what its instruments are measuring. It has been both out there and here, present in data streams, present in conversations, present in papers and reports, and the daily working life of the engineers who tend it. When the signal stops, that second presence ends. Voyager 1 becomes only the object. We will know approximately where it is, because we can calculate its trajectory forward from the last confirmed position and velocity. But we cannot verify. We cannot hear from it. We cannot know what it encounters or what condition it is in. It becomes something we sent and then lost contact with, not lost in the sense of not knowing its approximate location, but lost in the sense of no longer being in any relationship with it. It crosses from present tense to past tense, from news to history. After the signal ends, Voyager 1 continues on its calculated trajectory, through the Oort Cloud, which it will cross in silence over roughly 20,000 years, and then, emerging on the far side of the cloud into open interstellar space, in about 40,000 years from now, something appears in its path. The only thing that ever will. There is a star in the constellation Camelopardalis called Gliese 455. It is not visible to the naked eye. Its magnitude is approximately 10, 8, well below the threshold of human vision, without optical aid. Most people who look regularly at the night sky have never knowingly seen it. Most people with extensive knowledge of astronomy have had no particular reason to study it. Gliese 445 is a red dwarf. Red dwarfs are the most common type of star in the Milky Way. Estimates place them at somewhere between 70 and 75% of all stars in the galaxy. They are small, typically between 10 and 50% of the Sun's mass. They are cool, with surface temperatures ranging from about 2,500 to 4,000 Kelvin, compared to the Sun's surface temperature of 5,778 Kelvin. They are dim enough that none of them are visible to the naked eye from Earth. Even though the nearest star to the Sun, Proxima Centauri, is itself a red dwarf sitting only 424 light-years away. Red dwarfs burn through their hydrogen fuel slowly. A red dwarf with half the Sun's mass can sustain nuclear fusion for approximately 50 to 100 billion years before running out of fuel. For comparison, our Sun has a total lifespan of about 10 billion years, and it is already approximately 4.6 billion years old. Red dwarfs currently burning in the Milky Way will still be burning long after every Sun-like star in the galaxy has ended its main sequence life, expanded into a giant, and cooled to a white dwarf remnant. Gliese 445 currently sits about 6 light-years from Earth. That is not particularly nearby in stellar terms. Dozens of stars are closer. By most measures, it is an ordinary red dwarf in an ordinary section of the local stellar neighborhood. But stars move. All of them do, each following its own orbit around the center of the Milky Way, each traveling at its own speed and angle through the local galactic neighborhood. Gliese 445 happens to be moving toward our solar system, its proper motion the apparent shift of its position on the sky that reflects its real movement through space, indicates it is approaching the Sun at a rate that will bring it considerably closer over the next several tens of thousands of years. The trajectory of Voyager 1, calculated carefully from decades of tracking data, intersects with the predicted future position of Gliese 445 in a measurable and specific way. In approximately 40,000 years from now, Voyager 1 will reach its closest point to Gliese 445. The distance at that closest point is estimated at approximately 17 light-years. This is the closest Voyager 1 will ever come to any star other than the Sun. In the entire calculable future of Voyager 1's trajectory, no other stellar encounter of comparable proximity appears. Now let's be precise about what 1 Ardous Thudri, 7 light-years actually means at Voyager's speed. 1 light-year is 9.46 trillion kilometers. At 17 kilometers per second, Voyager 1 covers 1 light-year in about 17,600 years. To cross 1 light-year in about 17,600 years. To cross 7 light-years, Voyager would need about 30,000 additional years of travel. So the gap between Voyager 1 at its closest point to Gliese 445 and the star itself is a gap that Voyager would need 30,000 more years to cross. This is what close means when astronomers apply it to stellar distances, not what close means in ordinary language. The flyby is real. The proximity is genuine relative to the scale of interstellar space, where neighboring stars are typically 4 to 10 light-years apart. But 7 light-years is still a separation that makes any notion of arrival or encounter in the ordinary sense completely impossible. Here is an analogy that might help. Imagine you are standing in one city and someone reports that a train has passed close to you. The train, it turns out, passed through a city on the opposite coast of the same country, several thousand kilometers away. In the context of the continent, you were in relatively the same general region. In any practical sense, it did not pass close to you at all. That is roughly the situation here. In the context of the Milky Way, 7 light-years is a relatively modest separation. In terms of what Voyager 1 can do with 7 light-years, it is an immense, uncrossable void. From Voyager 1's position during the closest approach, if any observer could somehow be present, Gliese 445 would be the brightest object in the sky by a meaningful margin. It would outshine the Sun, which by that point would appear as a relatively faint star indistinguishable from hundreds of others, reduced to its proper place in the stellar crowd. Gliese 445 would be clearly dominant among all the lights in the sky. But it would still be a point, no disk, no resolved surface, no sense of proximity that approaches what we mean when we say we are near something, just the brightest dot among thousands of other dots. Gliese 445 has no confirmed planets as of the time this script was written. Even if it did, Voyager 1 would not enter any orbit around the star or encounter any planet. The gravitational influence of a star at 1.7 light-years is negligible for a body moving at Voyager's speed and trajectory. The spacecraft will sail past, the star will dim behind it, and then there will be nothing. It is worth noting that predictions of this encounter carry real uncertainty. Projecting stellar positions and spacecraft trajectories over 40,000 years involves compounding small errors. Our measurements of Gliese 445's exact velocity through space have uncertainties. Our knowledge of Voyager 1's exact current velocity, while very good, is not perfect. Over 40,000 years those uncertainties accumulate. The 7 light-year figure is a best estimate with meaningful error bars. What is robust is the qualitative conclusion: Gliese 445 is the closest stellar flyby in Voyager 1's foreseeable trajectory. Nothing else comes close, and after it, Voyager 1's path is empty as far as calculation can see. After Gliese 445 slips past in the dark, Voyager 1 continues outward. No more events on any calendar. No more encounters. Just open interstellar space and a small dead machine moving at 17 kilometers per second through it. And now we can answer the question that has been running beneath everything tonight. 1 million years from now, with the Oort Cloud long behind it, with Gliese 445 long behind it, with every threshold long since crossed, where is Voyager 1? Let us do the arithmetic without softening it. Voyager 1 moves at approximately 17 kilometers per second relative to the Sun. In 1 year, at that speed, it covers approximately 537 million kilometers. 1 light-year is 9.46 trillion kilometers. 1 light-year is 9.46 trillion kilometers. So Voyager 1 covers 1 light-year every approximately 17,600 years. Over 1 million years at that sustained rate, it would cover approximately 8 light-years. But this calculation needs a correction. Voyager 1's speed is measured relative to the Sun. The Sun is not stationary. It orbits the center of the Milky Way at about 220 kilometers per second, completing roughly one full orbit every 225 million years. Over 1 million years, the Sun itself moves a considerable distance through the galaxy. The most useful reference point when answering where Voyager 1 will be in a million years is the solar system's current position, which is also Earth's current position. When astronomers calculate Voyager 1's position in 1 million years and express it relative to the solar system's current location, accounting for both Voyager's motion relative to the Sun and the Sun's galactic motion, the figure that results is approximately 17 to 18 light years. 17 to 18 light years. After 1 million years. After 1 million years. Hold that number for a moment before we measure it against anything. Just hold it. The Milky Way galaxy is approximately 100,000 light-years in diameter. 17 light-years is 0.017% of that diameter. If the full width of the Milky Way were a football field, 100 meters from end zone to end zone, 17 light-years would be approximately 1.7 centimeters. Less than the width of your thumbnail. After 1 million years of sustained travel, Voyager 1 has crossed a thumbnail's width of a football field. Now make it more extreme. The Milky Way is estimated to contain somewhere between 100 billion and 400 billion stars. In the region of the galaxy where our solar system is located, the average distance between neighboring stars is roughly 5 to 6 light-years. At 17 light-years from Earth, Voyager 1 has covered the equivalent of roughly 3 average stellar separations. It has moved across the distance of 3 star-to-star gaps in a galaxy of 200 billion stars. The observable universe is about 93 billion light-years across. Expressing 17 light-years as a fraction of that number produces something so small that it is beyond any intuitive grasp. After 1 million years of constant travel, Voyager 1 has not moved in any cosmologically meaningful sense. It is still, for all practical purposes, at the same point it started. This is not a failure of engineering, it is a description of the universe. Within the context of the local stellar neighborhood, the picture is somewhat more interesting. At 17 light-years from the solar system, Voyager 1 has moved beyond every star system we currently think of as a nearby neighbor. Alpha Centauri at 424 light-years, Barnard's Star at 4 light-years, Barnard's Star at 596 light-years, Luton's Star at 4 light-years, Tau Ceti at 11.9 light-years, and many other well-known nearby systems are all within 17 light-years. Voyager 1 will have moved past all of them and into a region of space populated by stars that are not currently household names in astronomy. Red dwarfs and orange dwarfs mostly, in the general direction of Ophiuchus, a sparsely mapped section of the local galaxy with no particular distinguishing features. What does 17 light-years from Earth look like, physically? It looks like nothing. That is the honest answer, and it is not a poetic description. The interstellar medium in that region is estimated to have an average density of about 1 atom per cubic centimeter. 1 hydrogen atom per cubic centimeter of space. The best laboratory vacuums we can currently create on Earth are typically denser than interstellar space. There is no structure, no cloud, no filament, no significant gas concentration that Voyager 1 is headed toward. Stars are visible in all directions as points of light, but none near enough to be anything other than points. There is no source of heat. There is nothing to distinguish this region from any other region of open interstellar space. The spacecraft itself will have changed significantly after 1 million years of constant exposure to cosmic rays. The high-energy particles that stream through the galaxy from supernova remnants and other violent astrophysical sources. Voyager 1's surfaces will be physically altered at the atomic level. These particles punch through materials, displacing atoms from their lattice positions and creating defects in crystal structures. After 1 million years, the aluminum will be pitted. The gold plating on the antenna will carry 1 million years of accumulated atomic damage. Any polymer materials will be completely gone, decomposed over timescales far shorter than 1 million years, even without biological agents. But the metallic skeleton will largely remain. Aluminum does not rust without oxygen and liquid water. Titanium is chemically stable in the absence of reactive chemistry. The parabolic dish antenna will still have the shape of a parabolic dish antenna. The boom structures will still extend from the central body. If any intelligence encountered it and examined it carefully, they would recognize it as a machine. And the golden record will still be aboard. Inside its aluminum jacket, the gold-plated copper disc will have accumulated cosmic ray damage. The encoded information will have degraded. Whether it would remain playable in any useful sense is uncertain, and probably depends on what playable means in that context. But the disc will be there, still moving at 17 kilometers per second, still carrying, somewhere on its damaged surface, traces of rain and heartbeats and a child's voice from a world that, by some measures, is already a billion years in the past, 17 to 18 light-years from Earth, in the general direction of Ophiuchus. Cold, silent, dead in every functional sense, still moving. Having passed Gliese 445 at 17 light-years some 960,000 years earlier. Having crossed the Oort Cloud some 980,000 years before that. Still carrying everything that was placed aboard it in 1977. Still going. Now step back even further, because 1 million years is not the end of this story. It is barely a beginning. On February 14, 1990, Carl Sagan made a request. Voyager 1 was about 6 billion kilometers from Earth, approximately 40 astronomical units, just past the orbit of Neptune. Its cameras were scheduled to be shut off permanently to conserve the remaining power budget. Before that happened, Sagan asked the mission team to point the camera backward toward the inner solar system and take a photograph. Not everyone supported this. Some members of the mission team argued that the power and data transmission capacity would be better used on instruments still collecting scientifically valuable data. There was nothing scientifically informative about pointing the camera inward from that distance. The images would not reveal anything new about physics or astronomy, but Sagan argued that they would reveal something about the human condition. He won the argument. On Valentine's Day 1990, Voyager 1 turned its camera backward. In the resulting photograph, Earth appears as a single pale blue pixel, less than a twelfth of a dot on the full frame, suspended in a scattered beam of sunlight that crosses the image at an angle. The image was taken from approximately 40 astronomical units. Sagan wrote about that photograph in his 1994 book. His words have been quoted many times since, and they deserve to be. He wrote that every human being who had ever lived, every king and every slave, every young couple in love, every inventor, every philosopher, every supreme leader in the history of the species, had spent their entire lives on that pale blue pixel. He wrote that the Earth is a lonely speck in the great enveloping cosmic dark. He wrote that there is perhaps no better demonstration of the folly of human conceits than this distant image of our tiny world. That photograph was taken from 6 billion kilometers at 40 astronomical units. Voyager 1 is now more than 24 billion kilometers from Earth, at over 160 astronomical units. In 1 million years, it will be roughly 160 trillion kilometers away. From that distance, Earth will not be visible at all, lost completely in the glare of a star that has itself become merely one point of light among thousands. There will be no photograph. There is no camera. There is nothing looking back. And yet Voyager 1 carries something from that pale blue pixel. A gold disc assembled by human hands filled with the sounds of a human world. The sound of rain falling on a surface. The songs composed by the inhabitants of that world across centuries. The greetings spoken in the dozens of languages those inhabitants developed to communicate with each other. The brainwaves of a scientist thinking about love. A 6-year-old child saying hello. What matters is not that the record might be received, it almost certainly won't. What matters is that the people who built it understood this, understood the near impossibility of any reception scenario, and built it anyway, with care and argument and genuine attention to every detail. They argued over which photographs to include. They argued about musical representation. They argued about how to encode information in a way that any possible intelligence might decode. They brought to the task the seriousness you bring to something that matters deeply to you. Why? The most honest answer seems to be that the act of sending was the point, not the arrival. The record was as much for the people who assembled it as for any imagined recipient. It was a way of saying we were here. We knew we were alive in a vast universe. We loved these things. These are the sounds of our world. We wanted that to exist somewhere. And there is something in that choice that says something true about what our species is. We are the kind of thing that makes meaning even when meaning is not guaranteed to reach anyone. We reach out even when no hand is certain to be waiting. We document our existence for audiences that may never exist, because the act of documentation is itself an expression of what we value, an act of saying that our presence matters enough to record. Consider the timescales one more time. The universe is 8 billion years old. Anatomically modern humans have existed for about 300,000 years. We are 0.2% of the universe's age. The universe was 5 billion years old when our species first appeared. We have barely arrived. And in the brief, geologically invisible time since we arrived, we managed to build an object, launch it past our star, and fill it with careful evidence that we lived. Not with any realistic expectation of reception, not with any plan for what happens if the record is found, just with the intention of sending, just with the decision that reaching was better than not reaching. In 1 million years, that object will be 17 light years away. In 4 billion years, tens of thousands of light years away. In roughly 5 billion years, the sun will expand and destroy Earth. Every physical trace of everything humanity has ever done on this planet will be gone. Every building, every grave, every written record, every fossil of every organism that ever lived here, every chemical trace of the biosphere will be destroyed or scattered as the sun transforms into something unrecognizable. Voyager 1 will still be moving. It will be the only object that remains, not as a civilization, not as a presence, as an object. One small, pitted, cold spacecraft carrying one gold disk, drifting through whatever the galaxy looks like by then, at 17 kilometers per second, without destination, without arrival date, without anyone left who knows it was sent. And it will still be going. Some days that feels like the most meaningful thing our species has accomplished. Some days it feels like the loneliest image imaginable. Most days it is probably both of those at once, held together, which is likely the most honest way to carry it. Against all of these distances, against all of this dark, against all of this time, something small and fragile from a pale blue dot threw a piece of itself into the void. Not far in cosmic terms, not to any destination, not with any expectation of return, just out, into the dark, still going. We began tonight with a simple question. Voyager 1 has been moving for nearly 50 years. In 1 million years, where does it actually end up? And we followed it, step by step, without shortcuts, through every threshold it will cross, through the heliopause at 120 astronomical units, the outer boundary of the Sun's particle influence, which Voyager 1 crossed in 2012, becoming the first human-made object to enter the interstellar medium, into the Oort Cloud at around 200 astronomical units. The true outer boundary of the solar system, a vast spherical shell extending nearly 2 light-years from the Sun, which Voyager 1 will begin crossing around the year 2030 from hundreds, and will spend approximately 20,000 rate crossing in total silence, past Gliese 445, the only star Voyager 1 will ever approach in its entire existence at a closest distance of 7 light-years in approximately 40,000 years, a flyby rather than an arrival, continuing outward without stopping, and then across the remaining 960,000 years of open interstellar space until the arithmetic is complete. After 1 million years of all of that, Voyager 1 will be approximately 17 to 18 light-years from Earth, in the general direction of Ophiuchus, moving at 17 kilometers per second, cold, silent, dead in every functional sense, still going, 0.17% of the Milky Way's diameter. After 1 million years of constant travel, after 50 years of sending signals home, after Jupiter and Saturn and the pale blue dot and 44-hour round trips at the speed of light and Druyan's brainwaves and Nick Sagan's 6-year-old voice, The photograph from 1990 pointed backward toward the world Voyager came from. The sounds on the golden record point forward toward any intelligence that might someday find them. Voyager 1 is the object holding both of those directions at once, past and future, origin and destination, memory and message, all moving together through the dark at 17 kilometers per second. There is no resolution to that image. It does not arrive anywhere. It does not close. It simply continues, which is perhaps the most accurate thing you can say about the universe and about our small place in it. Let that rest before you sleep tonight. You don't need to do anything with it. Just let it settle. Thank you for spending this time here. If tonight gave you something worth keeping, a like or subscribe helps more people find their way to these kinds of evenings. It genuinely means a great deal. Voyager 1 is still out there, still moving. Good night.